Hello everyone, I'm Liu He from Tsinghua University. Today I'll present our work, SHyLA, 3D-Stacked NVM-DRAM Hybrid LLM-Inference Architecture Exploiting Data and Memory Heterogeneity. In cloud LLM inference, many users are served concurrently by an inference cluster. There are two metrics that pull against each other. With larger batches, system throughput tends to increase, but per-user throughput tends to decrease. And a typical service-level objective is 25 tokens per second per user. Therefore, the optimization goal is to maximize system throughput while satisfying per-user SLO constraints. However, memory capacity and bandwidth are bottlenecks in cloud LLM inference. Growing static weights and KV cache demand larger memory capacity, while the decode phase is memory-bound and demand high memory bandwidth. Therefore, we need both capacity and bandwidth at the same time. Prior works that enhance memory system often overlook either memory heterogeneity or data heterogeneity. In homogeneous memory system, DRAM-only designs provide high effective bandwidth but are capacity limited for large models and KV cache. In contrast, NVM designs offer large capacity but suffer from poor write performance and endurance. Existing NVM-DRAM hybrid systems mainly target general workloads, which primarily exhibit random access patterns. As a result, they achieve poor NVM bandwidth utilization, especially for writes. More importantly, they overlook LLM-specific opportunities, such as streamable reads that can better utilize NVM read bandwidth, as well as LLM data heterogeneity. Therefore, jointly exploit memory device and LLM data heterogeneity remains a missing opportunity. For memory heterogeneity, we study a DRAM-NVM hybrid system using phase-change memory as the NVM prototype for its maturity and stackability. We characterize DRAM and NVM along three dimensions: memory density, read affinity, and write affinity. First, NVM offers much higher density, about 4 times that of DRAM. Second, for reads, NVM can achieve DRAM comparable bandwidth utilization under sequential access with multiple banks, but both memories suffer low utilization under random access due to read latency. Third, for writes, NVM has around 100 times higher latency and orders of magnitude lower endurance than DRAM. In summary, DRAM has lower density but balanced read-write performance and high endurance. In contrast, NVM has high density and is sequential read-friendly, but suffers from poor write performance and endurance. LLM data is also heterogeneous. In LLM inference, there are 3 major data categories: static weights, KV cache, and input activations. We characterize them along 3 dimensions: data volume, data transaction, and write intensity. First, weight and KV cache are orders of magnitude larger than input activations. Second, weights have high read transaction but are write-free, while KV cache is also read-heavy with only light writes, since each KV cache element is written once per request. Input activations have relatively high read and write data transactions. Third, in terms of write intensity, input activations are written much more frequently than KV cache. In summary, weights are large, read-only, and streamable. KV cache is large, read-heavy, and streamable with infrequent writes. Input activations are smaller but read-write intensive. We jointly characterize memory and data heterogeneity along 3 dimensions: capacity, read affinity, and write affinity. DRAM and NVM have different strengths across these dimensions. Meanwhile, weights, KV cache, and input activations also have different requirements. This dual heterogeneity match guides our data allocation policy. Input activations are placed in DRAM, weights are placed in NVM, and KV cache is placed in NVM first, with spillover allocated to DRAM. Since weights and most KV cache reside in NVM and are read-intensive, a natural question is, can NVM provide sufficient read bandwidth? To answer this question, we look at the bandwidth capacity trade-off in memory design. Memory design offers flexibility. Under a fixed area budget, capacity can be traded for bandwidth. For example, allocating more area to peripheral circuitries and I/O improves bandwidth, but leaves less area for memory cells. Therefore, the bandwidth capacity design of a memory device is not a single point, but a curve. With 3D stacking, bandwidth can scale in 2D, further expanding the design space beyond 2D and 2.5D architectures with only 1D bandwidth scaling. More importantly, denser NVM can provide higher bandwidth with only modest capacity loss, which fits the massive and streamable reads in LLM-Inference. To fully unlock the potential of 3D-stacked NVM-DRAM memory, the first challenge is making the areal bandwidth of 3D stacking effective. 3D stacking provides high areal hardware bandwidth, but the effective bandwidth depends on utilization. In our design, LLM data is distributed across heterogeneous memory planes. However, each compute tile needs both DRAM reside input activations and NVM reside wait or KV cache to complete the computation. Without coordinated access, some memory planes can remain idle. Therefore, a dedicated data flow is needed to keep both DRAM and NVM planes active, converting 3D stacked areal hardware bandwidth into effective bandwidth. The second challenge is identifying the optimal design point. The design space is combinatorial. It includes hybrid memory design space, such as the NVM-DRAM area ratio and the bandwidth capacity trade-off of each memory type. It also includes the deployment space, such as batch and parallelism strategies. Moreover, the objective is constrained. We need to maximize system throughput under a per-user SLO. Therefore, we need an efficient design space exploration methodology to search the large constrained space and surface design insights. To address these challenges, we propose SHyLA, a 3D-stacked NVM-DRAM hybrid memory architecture with a bandwidth utilization-centric data flow and a two-stage DSC methodology. Here's an overview of the SHyLA architecture. SHyLA is a multi-chip module architecture that integrates multiple chiplets, where general-purpose processor and network processor work collaboratively. Each chiplet adopts parallel hybrid 3D memory stacking, placing side-by-side 4 high NVM and DRAM stacks on top of the compute die via die-to-wafer bonding. This allows each memory technology to independently optimize its bandwidth and capacity. At the bottom, the compute die contains 20 homogeneous compute tiles, with each tile physically mapped to the stacked memory plane above. Inside the compute die, we design hierarchical tile connectivity to support the dedicated data flow. All compute tiles are identical but are classified by the memory plane above. D tiles connect to DRAM planes and N tiles connect to NVM planes. D tiles and N tiles are then grouped based on their relative physical positions. Based on these tile groups, we design a hierarchical tile connectivity. The first level provides dedicated intra-group links to localize the dominant traffic between DRAM and NVM within the tile group. The second level is an intergroup AXI fabric, which handles occasional cross-group data redistribution to preserve full chip connectivity. This hierarchy forms the foundation of our dedicated data flow. To convert 3D stacked areal hardware bandwidth into effective bandwidth, we design a bandwidth utilization-centric data flow. It combines memory plane-aware data layout with layer-specific execution to minimize memory plane idleness. For FFN layers, weight columns are partitioned across NVM planes, and in-group NVM planes also serve the weights consumed by D tiles. Input activation rows are partitioned across DRAM planes. All tiles jointly compute 1 gem. For attention layers, the KV cache of an N-tile mapped attention head is stored in the NVM plane above that tile. For a D-tile mapped attention head, its KV cache is partitioned across the in-group NVM planes. If the KV cache exceeds NVM capacity, the overflow is stored in the DRAM planes within the group. The execution strategy is also phase-specific. In the prefill phase, all tiles collaboratively compute 1 attention head because the operation is gem-dominated. In the decode phase, each tile independently computes 1 head to exploit head-level parallelism. Overall, this data flow keeps heterogeneous memory planes active and improves the utilization of 3D stacked areal bandwidth. To find the system throughput optimal design under per-user SLO constraints, We search both hybrid memory configurations and deployment strategies using a two-stage DSC methodology. Stage 1 is system throughput-oriented, heuristic-based hybrid memory configuration determination. With heuristic deployment settings and fixed architecture parameters, it exhaustively searches the memory design space and selects the configuration with the highest peak system throughput. Using a hybrid memory design selected in Stage 1, Stage 2 searches the deployment design space. It applies a per-user throughput constraint evolutionary algorithm to find the deployment configuration that maximizes system throughput while satisfying the per-user SLO. Both stages use a fast analytical model to estimate system throughput and per-user throughput for each candidate design. On a 96-core Xeon machine, the full DSC finishes in about 10 to 15 minutes. The key insight from the design space exploration is that for large models with dense attention, an approximately 4:1 NVM to DRAM area ratio is optimal, with NVM balancing capacity and the bandwidth and the DRAM maximizing bandwidth. The figure shows a subset of the design space and the selected optimal point. We further study how model structure affects this design choice in the evaluation section. The reason behind is that weight and KB cache dominate runtime and require both capacity and bandwidth, so NVM receives most of the area budget. However, the benefit of additional NVM capacity eventually saturates. Once on-chip buffering, rather than batch size, becomes the data reuse bottleneck, the remaining NVM area is better allocated to bandwidth. For DRAM, the key requirement is to provide enough capacity for input activation storage. After that, the rest of the DRAM area is also optimized for bandwidth. With the design in place, let's look at the evaluation. We use GPU Sim, Cacti 3DD, and 3DIs for different simulation purposes. And our evaluated system include GPU baselines and DSA baselines besides SHyLA. In order to ensure the generalization of the results, our benchmarks includes 5 model variations with requests with different sequence lengths. We evaluate peak system throughput across sequence lengths, model sizes, and the model structures. System throughput is measured by the total runtime required to process a fixed number of requests. Across 40 workloads, SHyLA achieves 2.02 times and 1.76 times GeoMean peak system throughput gains over DRAM-only and NVM-only systems, respectively. To evaluate the effectiveness of bandwidth utilization-centric data flow, we compare SHyLA with and without the dedicated data flow. The results show that the data flow alone contributes to a 1.35 times improvement by better exploiting 3D-stacked array bandwidth. The evaluation results also show the advantageous scenario for SHyLA over DRAM-only. SHyLA gains most when memory capacity is the bottleneck, where its larger capacity enables larger batches and more weight reuse. These scenarios include long context requests, larger models, and denser attention. We will later show that NVM only is impractical due to poor write endurance and limited lifetime. We also evaluate system throughput under per-user SLO constraints. Here, the x-axis is per-user throughput and the y-axis is system throughput. The vertical red dashed line marks the per-user SLO. The results show that SHyLA consistently outperforms both DRAM-only and NVM-only designs. Another observation is that PD aggregation is consistently preferred over PD disaggregation. At a moderate system scale, disaggregation reduces the achievable batch size due to weight duplication. It also incurs costly KV cache transfer and additional NVM writes, which is a design-specific penalty in SHyLA. A natural concern with NVM is endurance, so we analyze both the write rate and the resulting lifetime. In SHyLA, only KV cache is dynamically written to NVM, while DRAM absorbs the frequent write operations from input activations. This reduces NVM write pressure and extends SHyLA's lifetime by about 15 times compared with an NVM-only system. Under an NVM endurance assumption of 100 million writes, SHyLA achieves roughly a 10-year lifetime. As for DSE analysis, we study how different model structure prefer different bandwidth capacity trade-offs in the NVM-DRAM hybrid memory system. For each model, we evaluate 19 requests with different sequence centers. The x-axis shows different NVM-DRAM bandwidth capacity configurations per memory plane, while the y-axis shows how many workloads prefer each configuration. The key finding is that the preferred memory design point is largely determined by attention sparsity. Models with sparse attention, such as GQA, favors NVM with higher bandwidth. Their lower KB cache pressure already enables large batches, so the benefit of adding more capacity quickly saturates. In contrast, models with dense attention, such as MHA, prefer a more balanced NVM bandwidth capacity design. Their higher KB cache pressure limits batch size, so additional NVM capacity still helps improve weight reuse. Let me wrap up with the takeaways. First, this work proposes a 3D-stacked NVM-DRAM hybrid architecture. Second, this work explores a dual heterogeneity match, align LLM data heterogeneity with NVM-DRAM device heterogeneity. Third, the effective bandwidth capacity trade-off in 3D stacking translates NVM density into real bandwidth, and the design space exploration determines an optimal 4:1 NVM to DRAM area ratio in hybrid memory design, with NVM balancing capacity and bandwidth and DRAM trading off for bandwidth. Fourth, data flow must be co-designed to convert 3D stacked real hardware bandwidth into effective bandwidth. That's all for my presentation. Thanks for your attention.